All right, so last time we looked at the rank nullity theorem. I think that's about where we finished off, where we said, suppose T maps from, say, some vector space V with, and let me make sure I keep the same letters. V with dimension n to W with dimension m. Then we said that the dimension of the kernel of T plus the dimension of the column, let's go ahead and just say the dimension of the image of T needs to be equal to n, the originating space. Remember, we also call this the rank. All of this together is the rank of the transformation, and that fits with the word rank as we used it before, because we used the word rank before to refer to the dimension of the column space, which is the same idea as we saw. So another way of saying this is that the number, and this is, I think this is the important takeaway when you're looking at the matrix that represents the linear transformation, is that the number of, so remember the kernel had to do with the number, we saw it had to do with the number of, well, let's just say, yeah, the number of free variables are specifically the columns that corresponded to free variables. Okay? So it was the number of columns associated with free variables plus the number of columns, well, pivot columns, and that has to equal n. And that should make sense. I mean, at that point, you have the total number of columns that you'd have in this matrix. So if we were to look back at this example, so here we've got a transformation that's going from R7 to R5. So we would expect then to have a 5 by 7 matrix, and that's what we have here. We've got a 5 by 7 matrix. We're multiplying it by a 7 by 1 matrix to give us a 5, or 7 by 1 vector, to give us a 5 by 1 vector. Okay? I think we put this up last time. Is that correct? You should have it in your notes. Okay. So let's just reiterate though. We notice that we've got, so the first column, that's a pivot column. This third column's a pivot column. This fourth column's a pivot column, and this fifth column's a pivot column. So we've got 5 pivot columns. Okay. So we know that the dimension for this example here, the dimension of the kernel of T is 5, and we know that the oops, is that 5? That should be 4, right? 1, 2, 3, 4. Yep. The dimension of the kernel of T is 4, and if we count up the number of well, the remaining vectors are. Did I do it again? 1, 2, 3, 4, 5, 6. Boy. Yeah. So let's see. We're missing 0, 1, 1, 0, 0. Then we have 0, 0, 0, 0, 1. Let's see here, but that's still a. Oops, that's not. That's still a pivot column, and then this corresponds to a free variable. So then we've got the dimension of the column space. Let's do this one more time. All right, the kernel corresponds to the number of free variables that we have, and we've got 1, 2, 3, so that comes out to be 3. And the dimension of the column space, or another way of saying that, the dimension of the image of T is in both these cases is 4, the number of pivot columns we have. Any questions on that? I feel like that rank nullity theorem sort of solidifies maybe something we were starting to suspect as we were working through this. There was a connection between our pivot columns and how big how big of a space we get in the vector space that we're moving to. That is the size of the image. Okay. Any questions on that? Okay. All right. So let's look at 2 more examples from this. This is still from section 5.2, so let's look at these 2 examples. So for the ODE, let's look at this ODE here. Y double prime plus y is equal to f of t. So here we've got a non-homogeneous, well, we shouldn't say that. We don't know what f of t is. We've got a second order linear ODE. Okay? We can think of this. First of all, as a linear transformation. And the fact that we can think of it as a linear transformation is related to the fact that it's a linear differential equation. Okay? So with every, this is an important thing to maybe jot down, with every linear differential equation, we can pair it with a linear transformation. Okay? So we can always think of a linear differential equation as having a linear transformation. And in this case, we're going to call it L2, and L2 is going to map from C2 of R to C of R. Okay? Folks, we've used this notation a few times, but we might have forgotten it. So remember that C2 is the twice differentiable functions. Okay? Being a little bit more careful, they're the functions that you can take the derivative of at least twice, and they're still, that C stands for what? Continuous. So they're the functions that you can take their derivatives twice, and you still get a continuous function when you're done. Okay? So we really should say continuous twice differentiable functions. And then all we're specifying, and one way to look at that is that when you do that, when you apply this linear operator, you just get a continuous function. Okay? So that's where this linear operator or this linear transformation lives. It's a function or a mapping from C2 to just C. And what does it do? It takes, you input a function that's twice differentiable, and you map it to that expression. So it gets mapped to whatever the left-hand side of the ODE is. Okay? So again, the way I look at this, and I think it's helpful for you to start drawing pictures of kind of abstract spaces. One way to look at this is, somewhere exists C2 over R. Okay, those are all the continuous twice differentiable functions. Okay. And over here you've got C of R. So it's going to take some function living here. What does that function look like? It looks like y, and it's going to map it over here to y double prime plus y. So this is the connection back into differential equations, and we'll see one more connection here in a little bit. But let's ask the question, what is the kernel, or what? Let's just say it like this, what is the significance of the kernel of L2? What is that significance? So first of all, what is the kernel? Remind me. Well, that's true if we've got an associated matrix, which we don't have in this case. We could come up with one, but we don't have it. It'd be kind of hard to come up with a matrix because there's so many different possibilities, but yes, that works. What else? So like, what is the actual definition of the kernel?
Zero transformation?
It's not the zero transformation, but it has something to do with zeros. We're working on it.
Set of all vectors in V that gets
Okay, so here's my coming from space. This is my domain space. This is my codomain space, right? And so the kernel is all the vectors in the domain space that get mapped to where? Well, not just the codomain, but what in the codomain? The 0 in the codomain. So somewhere in here lives a 0 vector, or in this case it would be the 0 function. And so we want to know what functions specifically get mapped to 0. Okay. Well, what do we call these in differential equation land? So we want L of y to equal what? We want L of y to equal 0. But what is L of y? It's y double prime plus y to equal 0. So notice, what did we start with? I mean, we just said we've got this differential equation here where f of t, that term there might be 0 or it might be any other function involving t, right? But what is the kernel of a differential, the linear transformation that's associated with the differential equation? What's the kernel of it? It's the homogeneous solutions. Okay? So these are precisely, these are the homogeneous solutions. Okay? Great. Questions on that, folks? So set example. Okay. So let's look at the non-homogeneous principle for linear transformations. So let's let T map from some vector space V to some vector space W. Be a linear transformation. And let's suppose V sub p, that's a vector, solves the equation T of V equals B for some B in W space. So what am I saying? I'm saying pick some, you've got some B existing in W space. So here's the picture. We've got V, we've got W. Okay. You've got some B here. And so we want V of P to get mapped to B. Okay. So suppose V of P solves that. Then I want to talk about all solutions to this. Okay? The set of all solutions to the equation T of V equals B. So this is something we've been doing all along. So don't let your eyes glaze over now that we're doing it with vector spaces. Okay? I found one solution to this non-homogeneous. Just assume that if B is not 0, then this is a non-homogeneous equation. I found one solution to it, right? What have we always done? We found one solution and added it to all what's? We found one particular solution and added it all to all what's?
Homogeneous.
The homogeneous solutions, exactly. Okay. So the set of all solutions, S is equal to V of P, that one solution, plus VH, such that VH solves T of V equals specifically the 0 vector, 0 vector in W. So by finding all homogeneous solutions, you then take any combination of your particular solution plus one of the homogeneous solutions, and you've got all solutions to this mapping. That is, that describes, you know, for instance, here's some other one, VP prime, that goes there. Okay? One way to look at that is you could just simply take one of the homogeneous solutions, VH, and add these two together to give you VP prime. Okay, so you can build them all from just one particular solution and all homogeneous solutions. So let's do that in an example. Let's express all solutions to x1 plus x2 plus 3x3 equals 4, x1 plus 2x2 plus 5x3 equals 6. 1, 1, 1, 2, 3, 5, 4, 6, okay? Well, this corresponds to a mapping, first of all, from what space to what space? What's that? From R3 to R2, right? So we can think of T as a mapping from R3 to R2. So this is our answer. Okay, by T of X, Y, Z gets mapped to. Well, I don't want to write like that. Let's just give the matrix. By T of U equals 1, 1, 1, 2, 3, 5. U1, or I'm using X, I guess X1, X2. I kind of want to use U's so I don't get them confused. Let's use U1, U2, U3. So that's how this transformation works, right? It takes a vector in 3 space, maps it to 2 space by this combination. Okay? But specifically, we're looking for, so really another way of phrasing this question. So this was our question, right? Another way of expressing this question is to say we're looking for the solutions to T of U equals 4, 6. That's how we can think of this question. Okay. So what do we need to do? Well, according to what we wrote in the line above, we need to come up with a particular solution and the homogeneous solutions. Okay. So here we go. Let's do it like this, but just by following our work that we've done before, we don't have to do any new work. So we're going to take 1, 1, 1, 2, 3, 5, but join it with 4, 6, just as we've always done. So let's see, this gives us 1, 1, 3, 4, 0, 1, 2, 2, I think. Let's see, -1, add down. Yeah, okay. Continuing to row reduce, or continuing to put it into RREF form, we get 0, 1, 2, 2, and then multiply this by -1, add up, we get 1, 0, 1, 2, correct? I think? Yep. Okay. So nothing's really exciting there. Okay. But again, we can now start to talk about the solutions, right? In this case, x3 is free, right? And then we have, that's from the last, or the non-existent row, because it's got a that column corresponds to a free variable, right? Okay. By the way, did we have to have at least one free variable for this transformation? Yeah, how come? Because we're going from 3 space down to 2 space. You have to have at least one free variable, right? So that, I mean, the dimension of the kernel has to be 1 or larger, because you've got to send send some of those vectors down to 0 in order to make this transformation work if you're collapsing into smaller dimensions. Okay? And then we get that x2 is equal to 2 minus 2x3, and x1 is equal to 2 minus x3, right? So another way to express this solution then is to say that the solutions in the form x1, x2, x3 are going to look like 2 minus x3, 2 minus 2x3, and x3. Okay? Now I'm just going to break this down. So this is what's going on here, folks. I'm just going to break this down into the particular solution and the solutions to the homogeneous. Okay? Well, one way you could get the solution to the homogeneous is to go back and do what? Set it equal to 0, 0, right? Right? Then I'd have 0, 0 here. But then when I do any row reduction with it, what am I going to get? 0, 0, 0, 0 here, right? So for the homogeneous solution, we're going to have it's kind of the exact same setup. So that's one way to think about it, but I'd rather just think about it this way. So we just wouldn't have these 2's here, right? Okay. So another way to see that is we could just go ahead and write it this way. We have 2, 2, 0 plus r times negative 1, negative 2, 1. And so we can think of this as the homogeneous solutions here, and this is the particular solution. All right, that finishes up section 5.2. And I've got the questions, the homework up for those, so I think we're good to go with that. Let's move on to section 5.3. Before we do this, though, folks, I want to motivate you for where we're going. Okay? So the author asked this story problem. I think it's section 6.2 of the text, okay? And I thought it was an interesting enough problem that it's worth kind of jotting down this problem. And by the time we get to 6.2, we'll be able to solve it based on these techniques. So his question, and I was thinking about this lately because it's getting cold outside. Okay, and his question went something like this. Okay, suppose you've got a house, 2-story house. And maybe you've got a heat source right here. So you've got heat radiating up. Okay. And let's suppose this house is insulated in such a way that if you were to be able to isolate the top floor and the outside, it would take 10 hours. Let me draw it the same way the author does. It would take 10 hours for the upstairs to reach the same as the outside temperature. Okay, so if there was no heat going into it, if you didn't have the bottom floor, it would take 10 hours for the upstairs to reach the outside temperature. And you could check that, I think, by the materials that it's constructed out of. So anyway. And then let's just say it's different, so you've got sort of different insulation on the bottom floor, and I think this is just to make the problem a little more interesting, but you've got different insulation on the bottom floor, and maybe it takes 5 hours for that difference to occur, for the two to completely equilibrate. And then let's say between the two floors it takes 2 hours. And then let's say that the top floor starts off with a temperature y of 0 is 60 degrees, and x of 0 is 70 degrees, and then outside, to make our lives easier, it's 0 degrees. Okay. So one thing we might want to come up with is coming up with an equation x of t, which would give the temperature, the current temperature at the bottom floor. Okay. then y of t, which gives the temperature at the top floor. So there's a nice, interesting system of differential equations. Okay? So we're in the process of developing the tools to solve this system. This is similar to the rabbit and fox predator-prey problems that we saw way back in section 2.6. Okay? In that we've got two rates of change that are dependent upon one another for these two unknown functions, and we want to solve for both of them simultaneously. Okay? And notice, I mean, these would be two separate problems that we could just solve individually by Newton's law of cooling if we didn't have this interaction between the two floors. Because that interaction between the two floors, it becomes a system that has to be solved as a system. Okay? So that's a motivating example for where we're going. I don't know if that fits with some of your classes in heat flow and whatnot, but I don't know. Anyway, there's that example. All right, so back to linear algebra. Okay? We need to introduce the terms eigenvalue and eigenvector, which are kind of the last two big linear algebra terms that we need for this course. Okay? So that's what section 5.3 is about. It's about eigenvectors and eigenvalues. And let me just motivate you. Let's see if we can figure out what those look like. So let's let T be a mapping from R2 to R2 by T of U is equal to A of U, which is equal to 3, 0, 2, 0, U1, U2. Okay. So we've got a linear transformation. Okay. What's important here is this, what we're discussing now only works for going from an n-dimensional space back to itself. Okay, from R2 to R2 or R3 to R3, we're mapping back into the same dimensions. Okay, so these are always going to be square matrices that we're dealing with in this section, as opposed to the previous section. Okay. All right, let's just go ahead and see one thing. If you want to start getting a sense of how a transformation works, what should you look at? What it does to the what's? Well, yeah, we're gonna pick some vectors from the domain, but what two would be the best two vectors to pick from the domain? 1, 0 and 0, 1, the standard basis vector. So let's just see what it does to the standard basis vector. So let's look at T of E1. That's going to be T of the vector 1, 0, right? So if we apply our transformation to it, we'll have 3, 2, 0. Oh, oops, folks, I'm sorry, I miscopied that. That should be 3, 2 here for the first row. U2, U1, U2. Oops, we're doing this to the vector 1, 0. So when we apply the transformation to this first basis vector, what do we end up with? Well, let's see here. We get 3 and 2. Oh, we knew that, didn't we? Didn't we know that? What do you get when you apply a linear transformation to the first basis vector? You get the first column of your transformation. And so what are we going to get when we apply it to the second basis vector? You get the second column. But what I want to look at here is actually, we're going to look at a picture of this. Okay? So normally we don't do this because it gets too cluttered. Now, the exception is that 3 brown, 1 blue, or whatever it is, those videos, he's able to do a linear transformation on top of itself, and you can actually see what's going on. Okay? I can't do that. I can't actually draw an entire coordinate system and then shift it all appropriately and have the two overlaid on top of each other. You just can't visualize it. Okay, I couldn't draw. Okay, but let's look at specifically what happened to that vector right here. Here's the vector. That's the vector 1, 0, right? The E1 vector. When we did the transformation to it, what did we end up with? We ended up with 3, 2. So let's see here. There's 1, 2, 3, 1, 2. So this vector, after the transformation, got moved to here. Okay. So we went from here to here by doing, let's see here, colors. We did, so this is, we did t to this, right? So we could call this one right here, this is t of E1. Okay, that's how, so t of E1 stretches this vector out over to here. Okay. Normally I can't overlay the two on top of each other, but I can do that when I'm doing R2 to R2, or R3 to R3, if I could draw that. Okay? All right, so let's see what happens to the second basis vector here, just for fun. Well, t of E2, we already know what is t of E2 going to be without doing any work. It's going to be that second column. Okay? So let's look at, I'm not going to try to put these all in one coordinate system. Let's look at that. So we take the vector 1, 0, 1, which is this vector right here, right? 0 in the x direction, 1 in the y, so that's our E2. And it gets stretched to 2, 0. Where's that? Oh, that's this vector over here, 1, 2. So it gets stretched over there. There's t of E2. Okay? All right, so just make sure you're comfortable with this. I'd like you to go ahead and draw out t of, let's have you guys do t of 1, 1. Mimic this picture, mimic this idea. Okay, so do t of 1, 1. All right, so there's three transformations, or there's looking at what the transformation did to three different vectors. Any questions on that? Okay. All right, so now we're building up to our point, okay, or we're ready to go with our point. I'd now like you to do the same thing, or I guess I'll do it. Let's look at t of 2, 1. Okay. Let's look at t of 2, 1. So that would be the same 3, 2, 2, 0 applied to 2, 1. When I do this, I get 8, 4, and you might be thinking, well, what's interesting about that? Well, let's look at 8, 4, that vector here. If I wanted to, I'm not saying why, but notice I could factor a 2 out of both of these. I could divide both of them by whatever I wanted. I can divide both of them by 4. And if I factor a 4 out, I'd be left with 4 of 2, 1. And what's interesting about that? No, not the determinant. What was our, and it's a little bit strange, what was our input vector? 2, 1. What did we get out? A multiple of 2, 1. Okay. That didn't happen, say, over here when we plugged in 1, 1. We didn't get some multiple of that. We didn't get something lying along this, oops, that was supposed to be blue. We didn't get something lying along this line here. It got moved completely differently. But let's look at what the transformation did to this vector here. We took the vector 2, 1. Let's see, we're going to 8, 4. Okay. So we took the vector 2, 1, 1, 2, 1. That was our initial vector right here. And when we did the transformation to it, what did we get out? Well, we got out 8, 4. 3, 4, 5, 6, 7, 8. 2, 3, 4. And we end up with a multiple of the vector we started with. All the other vectors that we checked, they got stretched and pulled somewhere else. This one, well, they got pulled somewhere else. This one just got stretched along its original trajectory. That makes it a special vector of this transformation. Okay? So we're going to call we call the vector 2, 1 an eigenvector. Because when we plug it into the transformation, we just get a multiple of that vector out. Okay? And in fact, we will call 4, that multiple that we got out, an eigenvalue. Okay? I can't remember what the word eigen means. I was going to look it up and I ran out of time. But I think it has something to do with the essence of the transformation is in this, what happens to this one vector. Okay? Now, this has another eigenvector, okay? And you can check, but if you plug in, so we did, which one we do? We did 2, 1. If you were to take negative 1, 2 and plug it in, you're going to get out 1, negative 2, which we could write as negative 1 times 1, 2. So this is the eigenvector. Because we got just a multiple, oops, sorry, let me see here. We plugged in negative 1, 2, we got, oh, yeah, that should be negative 1, right? So that's the eigenvector, and then that makes negative 1 an eigenvalue. Okay? We're not really sure why these are useful yet, but it turns out they are of fundamental importance to us. And in a way, we've actually already been studying them. Okay? All right, so let's give them as a definition. Okay, let's let T map from a vector space to itself. Okay? And I'm just going to do this for finite. We're just doing it for finite dimensional, so that's why I'm putting the n on there, so we know what the dimensions are. Okay? Then T has an associated matrix A, which is what? What's its dimensions? N by n. Okay. So it has an associated matrix. Okay. If there exists a vector V contained in Vn so that T of V equals some lambda V, for lambda contained in the real numbers. Okay, so that's exactly what we just saw, right? Let's look at our statement up above here as we're copying down this definition. We saw that when we took T of 2, 1, we got some multiple times that same vector. That's what I've expressed right here, right? We plug in V into the transformation, and we got out V times some multiple. Okay? Then we call V an eigenvector, and lambda an eigenvalue. And I'd rather say lambda, its eigen. They're related, they're tied together. Its eigenvalue. Okay. So I've already said this, but let's just say it one more time. Note, applying T to one of its eigenvectors just gives another multiple of that vector. That's interesting. Most of the time, those vectors get pushed or pulled or stretched along, or moved somewhere else in the plane. But this one just gets, so for example, this one here, red was our original vector. When we plugged it into the transformation, we got out green, but that's just some multiple. That's just a scalar multiple of that original vector. Okay? All right. So, oh, great. Would you mind closing the door? Thank you. Perfect timing. All right. So the question is how do we find eigenvectors? How do we find eigenvectors and values? Because I just happened to, I had you plug those two into the transformation, and we see now, okay, I see that they're eigenvectors, and I see what their associated eigenvalue is, but how did I know to plug those in? How did I know that would work? There's a lot of potential vectors out there to plug into this thing, and most of them are not eigenvectors. Okay? So how are we going to do that? Okay. All right, so this is something that I will test you on. So this will be a test question here. This is the process for finding eigenvectors. In fact, let me say specifically process for finding eigenvalues. Okay, so what you always do in this procedure is you always find the eigenvalue first, and then you can find its associated eigenvector. Okay? So here's what we want. Well, we want t of some v to equal lambda v, right? That's what it. So we're looking for a v that does that. That's what it means to be an eigenvector. Okay? But remember, with every linear transformation, we've got an associated matrix, right? So we could rewrite this as AV equals lambda v, where A is that associated matrix that we talked about. So now I'm going to go ahead and we're going to do something sort of like factoring here. So first thing I'm going to do is I'm going to subtract over lambda v over to the other side. By the way, it's always helpful to remind yourself what type of objects you're dealing with, because there's a slick little trick in here that you got to be careful with. What type of object is v? Well, it's an n by 1 vector, right? What type of object is A? It's an n by n matrix, but their product is again a n by 1 vector. So that's a vector. This is a scalar times a vector, which is again a vector. So I've got two vectors set equal to each other. So all's right with the world, right? Then I subtract this vector over, so that leaves me the 0 vector on the right-hand side there, right? So do pay attention to this. Now, notice that both these expressions here have a v in them. I would like to do something like factoring. Okay? But if I factor this out, please don't do this because this is dead wrong. If I factored this out, I'd be left with this, which is nonsensical. If you did factoring as we learned it in algebra, that would be nonsensical. How come? Because what type of object is this? A matrix. What type of object is this? It's just a number, right? You can't subtract them. Okay. But one way to do that, one way to actually make this work, is to think of this as AV minus lambda IV. Is that true? When I multiply this n by 1 vector by this n by n matrix, I'm going to get v itself, right? That just returns v times lambda. So I've got the same as the line before, but now I can factor this out, and everything makes sense, right? Because what type of object is this critter right there? It's an n by n matrix, right? That I'm subtracting from A. Okay. I was going to review this before I started doing this derivation. So let's review it now. This is off to the side. Okay. Yeah. Remember that A is invertible if and only if the determinant of A is 0, or excuse me, the determinant of A does not equal 0. I can't remember, do we use DET or the absolute values in here? We use the absolute values. If and only if the determinant of A is not 0. Okay, so those two I'm just reminding you of because they were part of that big theorem, the big theorem of chapter 3, But there was one other piece to the big theorem of chapter 3 that we haven't talked a whole lot about. But these were, remember, we listed all of the following are equivalent, and it was a long list. Okay? Here's one we haven't talked about in a while. And it said that the equation ax equals specifically 0 has only the trivial solution. Put another way, that only works if A is what we call non-singular, which is the same thing as being invertible, which is the same thing as the determinant not being 0, right? So these are all the same idea. Well, let's look at what we have up here, because this is the piece that we need. This is the part of the big theorem that we need right now. Look at this equation that we're trying to solve. Okay, we're trying to find whom in this? We're trying to find our eigenvectors, right? That's our goal, is to find those eigenvectors. Okay. Well, this is some matrix times a vector equaling 0. Okay? This will equal 0. This is true if, first of all, the vector is 0. Okay? But we don't want that. How come? Oh, that's because I forgot part of the definition. Sorry. Going back all the way up to the definition of eigenvectors, I should have said, way back here, when I said there exists a vector v and vn with v not equal to the 0 vector. I should have added that. So we don't want it to be the 0 vector, because it's uninteresting, right? Always the 0 gets mapped to what? 0. So it's always a multiple of itself. So that's not really an interesting insight into the transformation, the specifics of the transformation. Okay? So the other way that could happen, though, is if the product of this matrix and some non-zero vector comes out to be 0. Well, the only case in which that happens, so that's saying that we have other solutions to this, right? Or a minus lambda v equals 0v has solutions other than 0, other than the trivial solution. But if it has zeros other than the trivial solution, then it is singular. And so what do we know about this matrix? Its determinant is actually what? Its determinant would have to be 0, right? So that tells us that the determinant of a minus lambda, oops, folks, I dropped something there. That should have been a minus lambda I dropped the I, needs to equal 0. Okay? So, for most of your homework problems, you're going to immediately jump to something like this statement here. Okay? By the way, this entire thing is called the characteristic equation. Of the matrix A. So generally, you're going to jump straight to this characteristic equation. Okay? But on your exam, I am going to ask you to show how we came up with the characteristic equation using this procedure. Okay? Okay. So that's our characteristic equation. And by the way, we could call, the book does this, so I'll say it too. P of lambda equal to just the determinant of a minus lambda I, it calls the characteristic polynomial. Okay. So we've got all the critters down now. Okay? So I'm going to work through this, and I'm actually going to go all the way back. We're going to start back from scratch here. We'll start right. Well, no, we'll start. Where do we want to start? I guess we will start with the characteristic equation. Okay, so let's do this. For T mapping from R2 with A, its associated matrix. That matrix that we were just looking at, which was 3 2s 0. Find its eigenvalues. Find its eigen. Somebody else was doing this. I'm going to copy this. Find its eigen stuff. Its eigenvectors and its eigenvalues. Okay. So let's find its eigen stuff here. So what do? We look at the characteristic equation. What's the characteristic equation? It's the determinant of A minus some unknown lambda I. And we need to force this thing to be 0, right? We're going to force it to be 0, and that'll give us our eigenvalues, from which we'll be able to find our eigenvectors. So this is how this works. We'll take the determinant of 3, 2, 2, 0, minus lambda times the identity, 1, 0, 0, 1. I'm going to do this, I'll show all steps this time. Usually what I'll do is actually I'll jump to, I'll show you which line I'll usually jump to, but this would be 3, 2, 2, 0, minus lambda, 0, 0, lambda. And so we end up with the determinant of 3 minus lambda, 2, 2 minus lambda. Okay. Normally, when I come up with the characteristic equation, I might jot this down and then I'll jump directly to here. Okay. After I recommend do this a few more times. Do these two lines a few more times in your homework until you get comfortable with it. But then normally you'll just jump straight to here. You'll realize it always goes that way. Okay. So what is the determinant of this? Well, it would be 3 minus lambda. This is a nice 2 by 2, so we can do that crisscross method. So 3 minus lambda times minus lambda minus 2 times 2, right? That comes out to be lambda squared minus 3 lambda minus 4. So if we set the characteristic equation, or we look at the characteristic equation, we set it equal to 0, we get lambda squared minus 3 lambda minus 4 equal to 0. That happens at lambda minus 4, or lambda minus 4 times lambda plus 1 equals 0. So that happens for lambda equal to 4 or lambda equal to negative 1. Now, let's look at precisely what we did before. This was one of our eigenvectors. We plugged in 2, 1, and what did we get out? We got a multiple of 2, 1 out, right? What multiple? 4. And then we plugged in negative 1, 2, and we got a multiple of negative 1, 2 out. But specifically, what multiple? Negative 1. Do you see that we've just found our 2 eigenvalues? So this process is how you find the eigenvalues, and then you sort of repeat it to find the eigenvectors. Let's do that. Okay. So we've got, so these are our eigenvalues. Okay. Now that we've got our eigenvalues, we can actually go back to, we can go back to this expression right here to come up with our eigenvectors. Okay. So going back to that, we've got A minus lambda I times the vector V, our eigenvector, and we need this to come out to be the 0 vector. Careful here, folks. This is where I've been saying all along, you need to be careful with your objects that you're dealing with. We're back to the vector equation. We're no longer dealing with the characteristic equation, which was about determinants. Right? How do I know that this isn't determinants? I don't have the absolute values on it. This is back to a matrix equation, or a vector equation, depending on how you want to look at it. We're solving for the vector V. So let's go ahead and pick the first lambda value that we found, the first eigenvalue. I don't know, we had 4. Let's go with 4. Okay. So this gives us A minus 4 I times v, we need this to equal the 0 vector. So what does v1 and what does v have to be for this to be true? That's finding our one of our eigenvectors. Okay. So this would be, we had 3, 2, 2, 0, minus 4, I'll just write I. But then this is when we subtract 4i from this. So again, what does I look like? It's got entries along the diagonal. So the only entries here that change are the diagonal ones. So I subtract 4 from each of the diagonal entries. So I'll have minus 1. This stays the same. This stays the same. And I'll have minus 4 times v1, v2 needs to equal 0, 0. There's our matrix equation. How are we doing, folks? Okay. So let's go ahead and find v1 and v2. So we'll do that through row reduction. Okay. Something's going to happen here that always happens. So we'll do it the first few times, and then we won't really think our way through the entire row reduction. We'll just do the first half of it. Okay. So let's see here. We need a 1 in that position. So we divide everything by -1, and we get 1 minus 2, 0, 2 minus 4, 0. Continuing, we need a 0 in our underneath that pivot 1. So we get 1 minus 2, 0. We get a 0 there. So we multiply the first row by -2 and add down. That gives us 0, 0, 0. So that's the thing that will always happen when you're solving for a eigenvector. You'll always get a bottom row of zeros there. If you don't, you've done something wrong. All right. So what does that mean? Well, if we're thinking about solving for v1, v2, okay, then we just said that v2 is free and v1 is equal to 2v2. All right? Everyone okay with that? So that means our solution is of the form v2 is free, so we'll just put a 1 there, and v1 is twice that, so it's going to be of this form right here, some constant r times the vector 2, 1. Which should be one of our eigenvectors, the eigenvector paired with 4. If it's not, it's the same up to a scalar multiple. Okay? By the way, people may, if I ask two different people to give the eigenvectors, they might come up with 2 different actual vectors, but they will be scalar multiples of one another. Okay, so it just, in fact, so if you're mimicking an example in the book, do check that, because just because you don't have the same eigenvector, you might have an eigenvector. They're not unique, because any multiple of that would work too. Okay, all right. So I'm going to introduce this terminology here. I'm going to say that the eigenspace of lambda equals 4 then is the span of this eigenvector. So I just want to get that notation, that terminology out of the way right now. Okay? So for every single eigenvalue, you can give the eigenspace of it, which is going to be the span of its corresponding eigenvector or eigenvectors. You might have more than one eigenvector. Okay? In our case here, notice that we just have one eigenvector, right? Okay? Because we were able to describe v in terms of one free variable here. Okay? So we just have the one constant here that describes it. All right. So we got the eigenspace, the span. Okay, so that was our and any multiple of 2, 1 is an eigenvector of lambda equals 4. let's do again. So that was with lambda equals 4. For what was our other eigenvalue? For lambda equals what? -1. Okay. So I'll let you guys do that. I want you to find the eigenvector paired with the eigenvalue -1. Or eigenvectors. You might have more than one, but you won't. Looking at the characteristic equation, which is that determinant equation. So we get the row of all zeros as we did before. Any questions on that? So how do we give the eigenvector? Well, we see that x or v2 again is free, and then v1 would be what? It would be -1/2 v2, right? Right? You guys want to run through that? Okay with that? So I mean, we just think of that as okay. This is the equation. v1 plus 1/2 v2 equals 0. So we get that. Yep. Okay. So then we can think of this eigenvector then as some multiple of -1/2 and 1. Okay. I could leave the eigenvector that way. After all, that's how I found it. But usually I'm going to do something with these eigenvectors. So it's nice to give an equivalent vector here. And in my opinion, an equivalent vector, a nice way to do that would be to multiply both terms by 2, right? So again, if I do that, one way to look at that, so it's been a while since we've done this, let's do it. I could say, okay, I'm going to multiply it by 2 in, well, we could do it like this. We could say r times 1/2 times 2, negative 1/2, 1. And then we bring that 2 inside the vector, so we've got 1/2 r times negative 1, 2. But r stood for an arbitrary number, so this would still be r negative 1, 2. So if you're wondering how you could do it, so that's what I did. I multiplied both of them by 2, both components by 2. And that still gives me the same span. Okay. So again, so for A, for our transformation T, we have eigenvalues lambda 1 equal to 4 and lambda 2 equal to negative 1 with eigenvectors. I think do we get 2, 1, is that right? Or 1, 2? 2, 1. 2, 1. Okay. Is that what we had before, folks? Yes, 2. Okay. 2, 1 and negative 1, 2, respectively. Okay. Meaning you pair this eigenvalue with this eigenvector and this eigenvalue with that eigenvector. They have to go together. Okay. Questions on that? Okay. So we have a geometric intuition for what an eigenvalue and eigenvectors are. Okay. An eigenvector is one that you plug into the transformation of a m by n transformation, and it just gives you a scalar multiple of it. So that's the eigenvector, and its scalar multiple is its corresponding eigenvalue. So we know geometrically what they look like. We now know how to find them. We're still not really interested, maybe we're not. We're still not really sure why we care about them, but that's coming. So let's go ahead and just list some properties of eigenvalues. Some of these are just related to the definition. Some of them are a little more interesting. Okay. Lambda, so for A, an m by m matrix. M by m matrix of real values. So lambda is an eigenvalue of A if and only if it solves the characteristic equation. That's just the definition, or that's not the definition. That's what we got after we applied the definition. We solved that. We did that work. But that's the same thing as saying this one is the definition. Lambda is an eigenvalue of A if and only if, so this one is the definition, A minus lambda I V is the zero vector in D. Here's some other properties. A has lambda equal to 0 as an eigenvector or eigenvalue if and only if the determinant of A is 0. So the only times you'll have A will have 0 as an eigenvalue is if it's not invertible. And that's actually related to the problem as to why it's not invertible. So I've got a few more. A and AT have the same characteristic equation. if they have the same characteristic equation, then they're going to have the same roots to the same characteristic equation, so they're going to have the same whats. What are the roots of the characteristic equations? What's that?
Oh no, I was just thinking something. We'll have the same eigenvalue.
They're going to have the same eigenvalues. So A and its transpose have the same eigenvalues. Lambda is an eigenvalue of A, with lambda not equal to 0, then 1 over lambda is an eigenvalue of A inverse. If you know the eigenvalues of A, then you can come up with the eigenvalues of A inverse. And of course, that only makes sense if A is invertible, which only works if lambda isn't 0. So far. The eigenvalues of an upper or lower triangular matrix are just the entries along the diagonal. That's a really important fact. That gives an interesting connection between eigenvalues and determinants. In that for triangular matrix, we said the determinant of a triangular matrix was just the product of all the entries along its diagonal. And so for a triangular matrix, another way of saying it is its determinant is the product of all of its eigenvalues. It's kind of interesting. The author calls this one the eigenvector theorem. And we've got A as before. If lambda 1 through lambda n are, and this is an important word here, folks, are distinct eigenvalues with eigenvectors. Each one has an eigenvector associated with it, right? So I shouldn't say that. Each one, it may have more than one associated with it, but because these are distinct, then we only have one eigenvector, or the dimension of each one of these eigenspaces is 1. So each one of these eigenspaces can be described by just one vector. So then we've got n of them. Then, because these are distinct, V1, the set V1 through Vn is linearly independent. So put another way, as long as the lambda, or as long as the eigenvalues are all distinct, then you're going to have the eigenvectors, and one will never be a multiple of the other. Okay? Two eigenvectors, one will never lie on top of the other or in its span, because your eigenvalues are distinct. Okay? When the eigenvalues are not distinct, we run into all sorts of problems. and we'll tackle a couple of them as we go. And a couple I'll just say use other techniques. All right. What else? We could construct, so this is kind of continuing off number 7, we could construct the invertible matrix, and I'm gonna label it P equal to V1, V2, Vn. And the author doesn't give this a name, but I think it should have a name because we're going to use it. So I'd like to call it called an eigenmatrix. Okay, just to give it a name. So it's a matrix that's composed of what? All of its columns are what? Eigenvectors. Okay. So we can only do that, that's why it's sitting underneath 7 here. We can only do that if we have distinct eigenvalues. That's the only way this will be an invertible matrix. So we need it to be linearly independent. Okay. Okay, so let's kind of put some of these ideas together in one more example. At this point, we've only found one set of eigenvectors corresponding to a transformation. So let's look at this example here. Let's let T map from R3 to R3. By A equal to 1, minus 1, 0, 1, 2, 1, minus 2, 1, minus 1. And let's find the eigenspaces of A and the eigenmatrix. And I really should say an eigenmatrix because you can make many of these. Okay, so we're not going to do this one by hand. I'm going to ask my Mathematica to do this one. Okay? So let's set it up though. Okay? We know we're after the solutions to this equation here: 1 minus lambda, 1 minus 2, minus 1, 2 minus lambda, 1, 0, 1, and minus 1 minus lambda. That's what we're looking for, right? Anyone have any questions about what I just did? Yeah.
I guess that just sounds
Okay. Yeah. So that's from taking the A minus lambda I. That's what we end up with. Okay. All right. So this one would be kind of a pain to do the determinant for. Do you see that? Because you got to pick a row or a column, and everyone has a 1 minus lambda in it. I mean, it would take you a little while to do it. It's just computationally difficult, right? But we could do it. But I want to show you. I really do think, I haven't been spending a lot of time in here showing you how to use different types of technologies, but I do think you should play around. You need to be able to do what we do in class by hand, but also see if you find, start looking for computer systems or whatever that help you out. I'm going to go to Wolfram Alpha, and Wolfram Alpha can compute determinants through the command DET. And then you can go ahead and notice, actually, as I type it, it actually suggests, it shows you a typical matrix. That's how we'll do matrices. So we'll do open brace for the entire matrix, then open the first row, okay, and then help me out, folks. The first entry was 1 minus lambda. Is that right?
Yeah.
So I'll put 1 minus A, because I don't know what a lambda is in here. Okay, comma, and then we had what? 1, followed by negative what? 2. Negative 2. Great. Okay, that's the first row. So I closed the first row. Do you see that? Comma. I'm starting the second row. What was our next entry?
Negative 1.
Negative 1.
Comma 2 minus A.
2 minus A instead of lambda. Okay.
Comma 1.
Comma 1. Close that row. Comma next row. 0,
comma 1,
comma 1, comma
-1 minus a.
-1 minus a. So we've got a's along our diagonal here. So I close the matrix with that last curly brace, and then I close the command determinant with a bracket there. You could just actually type in determinant and then the entries, but I want to use this language because I'm going to have to do something with it after we compute it. So here it's computed the determinant. Okay, we find that it's minus lambda cubed plus 2 lambda squared plus lambda minus 2. So let's put that up. So that gave us, we found this to be minus lambda cubed plus 2 lambda squared plus lambda minus 2. In this case, factoring this isn't that hard. I could factor out, if I group, there's that old technique, factor by grouping. So if I group the first 2 terms together, and then group the last 2 terms together, I can factor out a minus lambda squared from this first grouping. That leaves me with lambda minus 2 plus, in a way, factoring out a 1 from that second grouping. We get this, so that gives us 1 minus lambda squared times lambda minus 2. So we get 1 minus lambda times 1 plus lambda times lambda minus 2. So we find that lambda equals 1, lambda equals minus 1, and lambda equals 2 are 3 what? 3 distinct eigenvalues. Okay. I could have also, if I wanted to, I could have asked my math lab to factor this. So again, I just want to show you, or Mathematica to factor this. So by putting the factor around it, and it can build on those commands, and there it gives it to me in factored form already. That's nice. But what I'm actually going to do here now is I'm going to take that determinant that we had, and I'm going to say solve. And what did we set that determinant equal to? We set it equal to, we multiply it by, so here's the matrix, here's the corresponding matrix. So we've got that matrix equation here, so I'm going to go ahead and enter in times V1, V2, V3, and we want that to equal, which my Mathematica wants 2 equal signs, 0, 0, 0, we're in 3 space here. Okay. 4, and I need to tell what to solve it for, so we're solving for V1, V2, V3. I can't remember what I get if I just do this. Maybe that's helpful. Maybe this is helpful, maybe not. Yeah. Solve. It's true. Yeah, oh great, this did the whole thing. That's pretty slick. Okay. It said for your first eigenvalue, this is the corresponding eigenvector. You got to interpret that, right? I mean, pick one of the 2 that's set equal to one another and call the one of them free. Usually we call V2 free, right? Or excuse me, usually we call V3 free. So we call V3 here, if we call that free, then V2 is always a 0, and then V1 is the same, so that gives us the eigenvector 1, 0, 1. Here they're both solved in terms of V1. That's a little bit frustrating, but we could do that. We could call V1 free. So we'd have V1 is itself, this is V2 is 2/3, V1 is 1/3, or V3 is 1/3. But I think it makes more sense to multiply everything by a factor of 3. And so you'd get 3, 2, 1 for that one. And then here we have everything's in terms of V1 here, so we'd have 1, 3, 1 for our third eigenvector. Okay? Yeah, please go ahead. Yeah, and I can zoom in on that code if you want. So folks, you do have to do these by hand, right? We did it by hand for a 2x2. We did it by hand for a 2x2. Okay. So you have to be able to do it by hand, but I mean, you guys are going forward to other classes. You're going to be doing other things. You need to be able to find these eigenvectors very easily. Okay? To be honest, we can do that one more time. If we just take our original matrix, so that's following the procedure that you and I have learned, but we could just say, Mathematica is such a powerful language. It used to be tough. You used to know how to code in it. Now you just type it. You just say find eigenvectors of. And that actually does a much nicer job than what we just did, but that doesn't. That in no way mimics the procedure that we've been learning, right? Okay. So that was. I just typed in find eigenvectors of. Yep. Yeah. So I highly encourage you to, I mean, folks, you should be using technology along the way, but you shouldn't be relying on it. If you find yourself relying on it, then you haven't learned the procedure, and you need to learn it. Okay? But you should be learning how to do technology too. All right. So let me know if you have any questions over that. All right. So we've got our eigenvectors. Okay. So we just saw. So for these three eigenvectors, we found, or for three eigenvalues, we found the eigenvectors. Here we had, let's see, when we had lambda equals 1, we had 3, 2, 1 for when lambda was 1. We had
3, 2, 1.
3, 2, 1 for when lambda was 1. And then for when lambda was minus 1, we had 1, 0, 1. And then for when lambda was 2, we found 1, 3, 1. Questions on that, folks? So the eigenspaces, so the book uses this notation, I think it's good notation. The eigenspace for when lambda is equal to 1 is equal to the span of this eigenvector here, 3, 2, 1. And the eigenspace for when lambda is equal to -1 is equal to the span of 1, 0, 1. And the eigenspace for when lambda is equal to 2 is equal to the span of 1, 3, 1. So there's our three eigenspans. And so again, the book didn't give this a name, but I think we need it. We've got an eigenmatrix. I'm going to use the letter P for it, for what's coming up. So we've got the eigenmatrix of 3, 2, 1, 1, 0, 1, 1, 3, 1. Okay? That eigenmatrix goes with A. Okay? So this is the eigenmatrix for our A value, or for our A matrix, which was associated with the linear transformation. How are we doing? Just give me thumbs up to. Is that a good thumbs up?
Oh, yeah.
You're not just saying, oh, let's get on with it. All right. Okay. So I'm not going to do much more in this section. Actually, that's it. Yeah, that's all I'm going to do. That's all I'm going to do. Oh, I do want to show you this. So, last thing in this section, we've been calling this the characteristic equation. We've used that term characteristic before, right? Where did we use that word characteristic? I think we even call it characteristic equation. When we were solving nth order ODEs, right? And we found the corresponding characteristic equation, and we found its roots. Okay? I once had somebody ask me the connection between these two ideas, and I didn't know the answer, but our author actually supplies the answer, which is really neat. There is a connection between the two uses of the word. So let's look at this example here. Okay? So if I said solve this equation, solve y double prime minus y prime minus 2y equals 0. We found, okay, our method for doing that is to say this is the characteristic equation. And we look at the roots of it, right? So this would be r minus 2, r plus 1 equals 0. So we get r equals 2, or r equals negative 1. And so we get then a solution of y equals c1 e to the 2t plus c2 e to the minus t. Right? That was chapter 4 stuff. So remember, at some point, though, we said, hey, we could take a second order linear ODE and transcribe it. We could create a system out of it. Remember doing that? Okay. We did some substitutions. So we're going to let x equal y, or sorry, let's let x1 equal y, and we'll let x2 equal y prime. Make sure I've got that. Those were the substitutions we made. Seems right. Yeah. Okay. Well, then if we take the derivative of x1, then that makes x1 y prime. But what is y prime? It's the same thing as x2, right? And if we take x2 prime, that's the same thing as y double prime, but that's equal to, if we just solve that equation up here for y double prime, we'd have y prime plus 2y, which is the same thing as x2 plus 2x1. So that's how we changed this second order linear ODE into a system of first order ODEs. We would think of it as x1 prime, x2 prime is equal to, we got to get our order right, 0, 1, 2, 1, x1, x2. Through that transformation, right? Okay. So I think you did have one homework problem like that. If not, we did it in class. Okay. But if we go find the characteristic equation of this matrix here, we're going to have the exact same characteristic equation. Let's do that. So this characteristic equation, so let's label this as A. So the characteristic equation of A would be minus lambda 1, 2, 1 minus lambda, determinant. And if we calculate that determinant, we end up with lambda squared minus lambda minus 2, which is the exact same equation as the characteristic equation was originally. So that's the connection between those two words, and that's a connection between those two ideas. Just kind of, which is worth showing. It's kind of interesting. Okay. Any questions on that? I did that real fast, folks, coming up with this. So here was our A, and then I immediately jumped to that characteristic equation. Was that too fast? We okay with that? That's that A minus lambda I determinant. Okay. All right. Okay, this is section, I'm going to do one example from section 5.4. And this is an example of decoupling a system. Once we jump into section 6.1, the author just starts giving the answers to things. He says, when you have this, you could do it this way. Okay? And it works, but I'd like to show you kind of the behind the scenes of what we're going to do in chapter 6. And so it's through this decoupling process. And this to me gives a really cool way to do nth order. This is a method that would work for nth order, sorry, I should say nth order, a system of n linear differential equations. So if you have a system of n first-order linear differential equations, this method will always work. It could be pretty tedious, but it will always work. Okay? Sorry, be careful. As long as you have n distinct eigenvectors, or n distinct eigenvalues, excuse me. As long as your eigenvalues are distinct. We'll see that. Okay, so now let's go ahead and actually solve a system. Here we are. We're going to actually solve a system finally. So let's solve the system x1 prime is equal to x1 plus x2, and x2 prime is equal to 4x1 plus x2. I.e., this is the system the vector x prime is equal to a vector x with a equal to 1, 1, 4, 1. So this is the system in matrix form. This is the system as a, how we normally write systems of equations. Everyone okay with that? That formulation of it? Okay. All right. So let's suppose P is an invertible n by n matrix. Then we want to change variables. By the substitution U is equal to P inverse of X. That's the substitution we want to do. Or put another way, X is P of U, which is the more natural way to write it, but that's how we're doing the substitution. Okay? So if this is the case, then X bar prime would be P U bar prime. I don't know if that's completely obvious to you or not. I had to work it out myself to see that worked. Okay? But if you're curious, that's true. And if you're curious about that, let me know and I can show you. Okay? So that means we could transform this system. So the system becomes, so x prime bar equals ax bar becomes P U bar prime. Careful, that's not an inverse there, right? You don't have inverses of vectors. It's a prime. P U bar prime equals A, and then I'm replacing X with P U bar. But we said that the only stipulation that we put on P is that it be invertible, n by n matrix. So we could write U1 bar, U bar prime as P inverse A P U bar. Okay. This is an important construct in linear algebra. When you go on to take your second course in linear algebra, you'll be working with this formulation quite a lot. Okay. So far I haven't said what P had to be, but let's let P be A's eigenmatrix. And let's see what happens. Okay, so remember that's the term eigenmatrix that I gave you before. Okay. So to save a little bit of time, I'm just going to go ahead and tell you then what P would have to be. So for A, which we said is this matrix 1, 1, 4, 1, you can check me, you can do the work on this. Okay. And we end up with, we have lambda 1 would be 3, and lambda 2 is equal to -1. Okay. So this has eigenvectors. I'm going to just start using the abbreviation EV for eigenvectors, which has eigenvectors for 3. I got 1, 2, and for -1, I got negative 1, 2. So those are the eigenvectors. So that would make P then, the eigen, what I'm calling the eigenmatrix, it would make it 1, 2, minus 1, 2. Okay. Does everyone feel comfortable? I'm not showing all the details here because we're starting to run low on time. So given this matrix, could you find its corresponding eigenvalues? Yes, you look at the characteristic equation. Then once you've got each eigenvalue, you have a system of equations to solve to find the corresponding eigenvectors. Once you've got those two eigenvectors, you can put them together into what I'm calling the eigenmatrix. Okay? So let's look what happens now. We said that U1 bar could be written at, or U, sorry, keep putting the 1 on there. U prime bar is equal to P inverse A P U bar. But we just said that P is, the P that we're going to use is 1, 2, minus 1, 2. Is that going to be invertible? It's a good question to ask. Is that going to be invertible? Absolutely. How come? How many eigenvectors did we have? Excuse me, how many eigenvalues did we have? 2, and they were distinct, right? So this system, or sorry, this matrix that's made up of the 2 eigenvectors has to be invertible because these columns have to be linearly independent because they came from distinct eigenvalues. So absolutely this matrix is invertible. Okay? And in fact, P inverse, if you do the inverse process with it, we get 1/2 minus 1/2, 1/4, 1/4. Okay. So if we go ahead and compute this product, we've got 1/2, 1/4, minus 1/2, 1/4, times our A, which was 1, 1, 4, 1, times our P, which is 1, minus 1, 2, 2, times our U1, U2. Remember, let's not get lost in the forest here. We started with this original system of equations, but we did this substitution of variables by multiplying x bar by multiplying x bar here by P inverse. That's our substitution. Okay. It's not entirely clear why we've done that. That shouldn't be clear at this point. Okay. But it is a substitution, so solving this system, finding the solutions in terms of u will be equivalent to finding the solutions in terms of x. Okay. But when we do the matrix multiplication here, when I multiply the first 2 together, I'll multiply the 2 on the right together. So let's see here. This gives us 3 minus 1 is 1, 6, and minus 2. Oops. Hey folks, if you see me put that prime mark down below, let me know. When we do this last one, I'm going to actually write this out here. Let's see here. This would be 3/2 minus, or excuse me, 3/2 plus 6/4, right? And then we have 1/2 minus 2/4 for that entry. This entry would be minus 3/2 plus 6/4, and this entry would be minus 1/2 minus 2/4. U1, U2, and it is still not clear why on earth I'm doing this, but we end up with U bar prime is equal to 3, 0, 0, 1. And the take-home, there are 2 take-home points here. The first is, when we did this, we got a diagonal matrix. This is the first take-home point. So P inverse AP is a diagonal matrix. That's not unique to the problem we just did. That will always happen if we have indistinct eigenvalues and we form the corresponding eigenmatrix, then we will always get this to be a diagonal matrix. Okay? Okay, so this is where this corresponds to larger problems. You could now solve n by n like this. I'm just doing it for 2 by 2 because it takes enough time. Okay, but you could now solve n by n like this. Okay? But more importantly, I don't want to ever have to do that again. That was really, really tedious, right? Look at this. Oops. Sorry, I messed up my addition here. Let's see here. This is 3 halves plus another 3 halves. That's 3. That works. 1/2 minus 1/2. That's 0. Minus 1/2 plus 1/2. That's 0. But look, I messed this one up. This should be minus 1/2 minus 2/4. That should have been minus 1.
Isn't it 3 halves plus 2/3? Oh, that's 6/4.
6/4. Yeah. Yeah, I think we're okay. Okay? So not only this, not only the diagonal matrix, but who are the entries on that diagonal matrix? What are they? They are the eigenvalues. So not only that, but these are the eigenvalues of matrix A. So now I don't ever have to do this again, this P inverse times A times P. I know that when I do that multiplication, as long as I have distinct eigenvalues, it will always come out to be this diagonal matrix here. And here's the point. Why did we do this? Because we started off with a system of coupled differential equations. But look at this now. What is this corresponding system? Let's take it out of matrix form. This says U1 prime U2 prime is equal to 3U1 minus 1U2. But that system is this. Here's the first entry in the system. U1 prime equals 3U1. And here's the second entry. U2 prime is equal to minus U2. It's no longer coupled, right? So if you look at the original system with x's, we said x1 prime is the sum of these two unknown functions, and x2 prime is the sum of these two unknown functions. That would have been a mess to try to tease out. But by doing this substitution, we still have two differential equations, but they're separated. They're decoupled is the phrase we use. And so this is just an elementary first order differential equation, which we learned how to solve on day 1. We get that U1 of t is equal to C1 e to the 3t. And we get that U2 of t is equal to C2 e to the minus t. Now we're not done, because what did I just find? I just found the unknown functions U1 and U2, right? But I now need to get back to x land, right? Well, we said, though, that x bar was equal to p u bar. So that tells us that x1 and x2 is equal to, what was p? Well, p was our eigenmatrix, way back up here. P was our eigenmatrix, 1, 2, minus 1, 2, times our u1, u2, but we just said u1 is c1 e to the 3t, and u2 is c2 e to the minus t. And so that tells us that x1 of t is equal to, doing the matrix multiplication, c1 e to the 3t minus c2 e to the minus t. And x2 of t is 2c1 e to the 3t plus 2c2 e to the minus t. And here we have the point. I mean, because that was tedious. We got through it, we decoupled the system, we went into U-land, solved the system, came back. But look what the answer ends up being. What is 3? It was one of the eigenvalues. Here's 3, there it is. And what was minus 1? It was the other eigenvalue. But more importantly, if I write this in a different format, we put it back into matrix form, we've got x, x bar, just as a vector, is equal to, and we've got c1 e to the 3t times 1, 2, plus c2 e to the minus t times minus 1, 2. And who are these vectors right here? So these were the eigenvalues, and these were the eigenvectors. Why do we want to know eigenvalues and eigenvectors? Because they are the solutions, then the matrix, the corresponding, the matrix that corresponds to our system of differential equations, as long as, and this is important, as long as it has n distinct real eigenvalues, we can give the solution that way, and we don't have to do the work again. In the next class, we'll look at the case when we have repeated eigenvalues and when we have complex eigenvalues, because we're solving equations and you can have complex answers. All right, folks, I put up some problems for these two sections for next week. Okay. And that's all I've got. If you've got questions, please come by and see me. And remember, we've got some homework due on Thursday. Thank you very much.
So I just want to go through, there's a lot of extra stuff that I was writing down
Oh, yeah.
for the proof.
Uh-huh. Good.
The proof is this portion, obviously.
And as well as this part.
Oh, this whole part?
Yep, yep.
Kind of explain that.
Yeah, so what you would do is, let's see if we can, let me stop this